Hey everyone, welcome back. Hope you're doing well. In this video, we're going to walk through a few examples of schedule crashing. First, let's go through example 1 together. We are given a project with both duration and cost information for its activities. Now, let's take a closer look at the table provided in this example. This table summarizes the essential information we need for schedule crashing analysis. It includes several columns. The first column shows the activity ID representing each task in the project. The second column lists the predecessors, indicating the sequence of activities. In other words, which tasks must be completed before others can begin. Column 3 presents the normal duration of each activity, which is the standard time it would take to complete that task under regular conditions. Column 4 shows the minimum duration, which is the shortest time we could potentially complete the activity, assuming we apply schedule crashing techniques such as overtime, extra labor, or better equipment. Now, moving to column 5, which is max crash duration. This value is not given, so we need to calculate it ourselves. It simply represents how much we can potentially reduce the activity's duration. To calculate it, we subtract the minimum duration from the normal duration. This tells us the number of days available to crash each activity. Column 6 contains the normal cost, which is the cost to complete the activity under standard conditions. Column 7 lists the maximum cost, which represents how much the activity would cost if we reduced its duration to the minimum possible, typically involving overtime pay, extra crews, or other crash measures. Column 8 is another value we need to calculate, the unit crash cost. This tells us how much it will cost to crash each activity by 1 day. The formula is straightforward. Unit crash cost equals max cost minus normal cost divided by max crash duration. This value is key in helping us decide which activities to crash first. We usually prioritize those with the lowest unit crash cost on the critical path, since they give us the most time savings for the least additional cost. So in summary, we will need to fill in columns 5 and 8 through simple calculations using the given durations and costs. Once complete, we'll be able to evaluate the trade-offs between time and cost and begin the crashing process strategically. Note that the cost data given in the table is direct cost. For indirect cost, we are also told that overhead is $250 per day. Also, the liquidated damages are $500 a day, which will be charged if the project takes longer than 6 days. With this information, the question is, what is the optimal duration of the project? To find that, we'll need to complete the table by calculating columns 5 and 8. Then we apply the schedule crashing procedure, starting with column 5, max crash duration. This is calculated by subtracting the minimum duration in column 4 from the normal duration in column 3. For example, for activity A, we take 8 days minus 6 days, which gives us a max crash duration of 2 days. For activity B, 6 minus 4, also 2 days. And for activity C, 4 days minus 2 days gives us 2 days as well. Now let's move on to column 8, unit crash cost. To calculate this, we subtract the normal cost from the maximum cost, then divide that result by the max crash duration we just calculated. For activity A, we take $2,800 max cost minus $10,000 normal cost, which equals $800. Divide that by 2 days, and we get a unit crash cost of $400 per day. For activity B, $5,000 minus $4,000 equals $1,000. Divided by 2 gives us $500 per day. And for activity C, $6,800 minus $6,000 equals $800. Divide that by 2, and we again get $400 per day. Now that we have all the necessary data, we can move on to the next step, figuring out which activities to crash, starting with those on the critical path that have the lowest crash cost per day. Let's go through the first iteration of the schedule crashing process. Step 1, first, we identify the crashable activities. In this case, activities A, B, and C are all crashable as their max crash duration in column 5 are greater than 0. Step 2, next, we identify the critical path. From the network diagram, the critical path runs through activity B and activity C. Although there is another path that goes through activity A, it is not a critical path because its duration is 8 days, which is shorter than the 10-day duration of the path through B and C. Step 3, now we look at the crashable activities on the critical path and choose the one with the lowest unit crash cost. Between B and C, activity C has the lowest crash cost at $400 per day. Step 4, so we crash activity C by 1 day, reducing its duration from 4 days to 3 days. Step 5, then we calculate the crash cost, which is $400. We compare this with the cost savings, which includes $250 in daily overhead plus $500 in liquidated damages avoided, a total saving of $750. Since the crash cost of $400 is less than the saving of $750, this is a good move. Then we proceed with the crash and update the schedule. We find that the sequence start, B, C, finish remains the critical path, with a total duration of 9 days, 6 days for activity B, and 3 days for activity C, which is longer than the 8-day path through activity A. Now we move on to the second iteration. We begin again by identifying the crashable activities, which are still activities A, B, and C. Among them, activities B and C are on the critical path, as determined after the first schedule update. Next, we evaluate the crash costs. Activity C has the lowest crash cost at $400 per day, so crash it by 1 day, reducing its duration from 3 days to 2 days. After this, activity C becomes non-crashable. We now calculate the cost-benefit analysis. The crash cost is $400, while the savings from reducing activity B and C's durations are $750, $250 from overhead, and $500 from liquidated damages. Since the savings exceed the crash cost, it's beneficial to proceed with crashing activity C. With this decision, we move on to next step. Step 6, update the schedule. We can find that the path through activity A is now a critical path, as it has the same duration as the path through B and C, both of which have a total duration of 8 days. Now we do the third iteration, where we will continue evaluating and crashing activities as needed. Moving on to the third iteration, we begin by identifying the crashable activities. In this case, activities A and B are crashable, while activity C is no longer crashable. Next, we identify the critical activities. We now have 3 critical activities on 2 critical paths. Activity A on the first path, and activities B and C on the second path. To reduce the project duration by 1 unit, we need to crash both critical paths. We then evaluate the crash costs for each critical activity. Activity A is the only critical activity on path 1 with a crash cost of $400 per day, and activity B is the only crashable activity on path 2 with a crash cost of $500 per day. Remember that we need to crash both critical paths. We decide to crash activities A and B by 1 day. This reduces activity A's duration from 8 days to 7 days, and activity B's duration from 6 days to 5 days. Now we calculate the crash cost and compare it with the savings. The total crash cost is $400 from A plus $500 from B, totaling $900. The savings are $250 from reduced overhead and $500 from reduced liquidated damages, totaling $750. Since the total crash cost, $900, is greater than the total savings, $750, we decide not to proceed with this iteration. The cost-benefit analysis shows that crashing would not be beneficial. In conclusion, crashing activities A and B is not worthwhile. Since the crash costs exceed the savings, it is not a good move to proceed with this iteration. The schedule obtained at the end of the previous iteration remains our optimal schedule. Alright, we finally get the optimal project schedule by crashing activity C by 2 days, which helps reduce the project duration by 2 days. The original project duration is 10 days, and by crashing, we bring it down to 8 days total. However, we also need to keep in mind that the contract includes liquidated damages, a penalty of $500 per day for any duration that goes beyond 6 days. So we still have to account for liquidated damages. Now, let's calculate the total project cost for this 8-day schedule. It is the sum of the total normal cost, overhead, crash cost, and liquidated damages. The normal costs are $10,000 for activity A, $4,000 for activity B, and $6,000 for activity C. Next, we add the overhead, which is $250 per day for 8 days. We're also crashing activity C by 2 days at $400 per day, resulting in a crashing cost of $800. Since the project finishes in 8 days, exceeding the 6-day limit, we incur 2 days of liquidated damages at $500 per day. Now, adding everything together, we get the total project cost is $23,800 for the 8-day duration. This is the lowest project cost possible. If you shorten the project further, it will cost more than $23,800 to complete. Alright, let's go through another example that's a bit more complex. You are given a precedence diagram schedule with 5 activities labeled A to E. The schedule includes the normal, non-crashed durations, along with early start, finish, and late start and finish times. The table below shows the normal durations and normal costs for each activity under standard conditions. It also provides the minimum possible durations when crashing is applied, as well as the maximum costs associated with crashing to those minimum durations. The last column shows the crash cost per day, calculated by subtracting the normal cost from the maximum crash cost and dividing that by the difference between the normal and minimum durations. Activity A is a non-labor task whose duration depends on an external approval process. Therefore, it is not crashable. All other activities are labor-based and can be crashed. As a result, the table does not include crash cost or crashing data for activity A. Additional information provided includes a liquidated damage of $225 per day for project completion beyond day 7, and indirect costs of $75 per day. Our task is to determine the optimal project schedule that minimizes the total project cost, including direct costs, indirect costs, and any penalties. First, let's identify the critical path. From the network diagram, you can quickly see that activities A, C, and E form the critical path. This is because they have the same early and late start and finish times. You can refer to the videos on the precedence diagram method, PDM, for a refresher on how to identify critical activities. The next step is to find the critical activity with the lowest unit crashing cost. Since A, C, and E are on the critical path, we examine their crashing costs. Activity A is non-crashable because it's a non-labor approval task, so we exclude it. Between C and E, activity C has the lower crashing cost per day, $150 compared to $200 for E. So we crash activity C by 1 day. This reduces its duration from 3 days to 2 days. Crashing C by 1 day costs an additional $150, but we save a total of $300, $75 from reduced overhead, and $225 from reduced liquidated damages. Since the savings outweigh the cost, this move is economical, and we proceed with it. After rerunning the forward and backward pass, we get an updated network. At this point, the project duration becomes 10 days. The critical path remains A, C, and E. However, activity C is now at its minimum possible duration, so it can't be crashed any further. Moving on to the second iteration, the critical path still includes A, C, and E. But since A and C are non-crashable, only activity E can be crashed. Crashing E by 1 day costs $200. Again, we save $300 in total, $75 from overhead, and $225 from liquidated damages. Since the cost is less than the savings, this step is also economical. After crashing E, we rerun the PDM calculations, including forward pass and backward pass. The project duration drops to 9 days, and we find that the network now has 3 critical paths: the original path ACE, a new path ACD finish of E, and another path ABD finish of E. On the third iteration, we got to crash all these 3 critical paths to reduce the project duration by 1 more day. Note that activities A and C are still non-crashable. Also, the finish of E is just a point in time, not a task, so it has no duration and cannot be crashed. On the first path, E is the only crashable activity. On the second path, D is crashable. Since D also appears on the third path, crashing D by 1 day will shorten both paths 2 and 3 simultaneously. Therefore, we would need to crash E and D each by 1 day. Now we calculate the cost. Crashing E and D cost $200 and $150 respectively, totaling $350. The savings remain $300 from overhead and liquidated damage reductions. Since the cost exceeds the savings, this third iteration is not economical, and we do not proceed with it. As a result, the previous step gives us the optimal solution. The optimal project duration is 9 days after 2 crashing iterations. In the first iteration, we crashed C by 1 day, and in the second iteration, we crashed E by 1 day. Now, let's calculate the total project cost. The total normal cost from the original table is $4,200. The total crashing cost is $150 for crashing C and $200 for crashing E. Overhead costs are calculated as 9 days multiplied by $75 per day, which equals $675. Finally, we pay liquidated damages for 2 days over the 7-day limit at $225 per day, totaling $450. Adding everything together gives us a total project cost of $5,675. Alright, that wraps up this video where we walked through 2 examples of schedule crashing. Thanks for watching, and I'll see you in the next video. Goodbye.